A paper dropped last week in Science Advances, and I think it might change how you think about every single movement you make for the rest of your life. Not because it discovered some new brain region, not because of some drug, but because it proved that your body's doing math you never asked it to do, and it is doing it faster than you can blink. Here is the setup. You are reaching for something, a cup of coffee, your phone, whatever. And right in the middle of that motion, something unexpectedly good happens. A notification you were hoping for, a compliment, anything. What these researchers found is that within 220 milliseconds, roughly a fifth of a second, your body physically speeds up. Your arm moves faster, your muscles get a tiny burst of extra energy, and you have zero awareness that it happened. 220 milliseconds. That is faster than a conscious thought can form. Your brain evaluated what just happened, decided it was better than expected, and injected a little turbo boost into your movement, all before you had any say in the matter. Now you might be thinking, okay, good things make you move faster. That is not exactly breaking news. And you would be half right. We have known for a while that when you expect a reward, you tend to move faster toward it. That part is old science. If someone puts a $100 bill on the table and says, go get it, you are going to reach for it quicker than if they put a penny there. Your brain automatically calibrates your speed based on how much it thinks the goal is worth. The senior researcher on this study, Ala Ahmed at the University of Colorado Boulder, has this great example. When you go to the airport to pick up your parents, you might actually run to greet them. But if you are picking up a colleague, you are probably just going to walk. That is expected value shaping your movements. And that has been documented. But what this new study found is something different and honestly more interesting. It is not about what you expect. It is about what surprises you. The technical term is reward prediction error, the difference between what your brain predicted would happen and what actually happened. And the key insight from this paper is that this prediction error, this surprise signal, does not just update your beliefs about the world. It does not just teach you for next time. It physically changes how you are moving right now, in real time, within a fifth of a second. So let me walk you through what they actually did, because the experiment is surprisingly simple, and that is part of what makes it convincing. They had 64 people grip a robotic arm, basically a very precise joystick, and make reaching movements toward targets on a screen. 4 targets, each one secretly assigned a different probability of giving a reward: 0%, 33%, 66%, or 100%. And the reward itself was nothing fancy, just a little beep and a flash of light when you hit the target. In the second experiment, they added a small cash bonus to make it count a bit more. Now here is what is clever about this design. Because the targets have different probabilities, the brain starts building expectations. If you have been reaching toward a target that pays off 2 out of 3 times, your brain learns to expect about a 66% chance of reward. So when that target does pay off, it is a small positive surprise. When it does not, small negative surprise. But when the target that almost never pays off suddenly does, big positive surprise. And when the guaranteed target pays off, no surprise at all. You expected it. So what happened? First, the expected part. People move faster toward higher reward targets. No shock there. But then came the new finding. After the reward feedback arrived, in the return phase of the movement, the researchers detected a change in velocity that tracked exactly with the size and direction of the surprise. Positive surprise, unexpected reward, the arm sped up. Negative surprise, expected reward that did not come, the arm slowed down. And when the reward was totally predictable, 100% certain, nothing. No boost at all. The reward happened, the brain said, yeah, I knew that. And the arm kept moving at the same pace. This is worth sitting with for a second. It means your body does not just respond to good things happening, it responds to good things happening that it did not see coming. The surprise is the trigger, not the reward itself. And the timing is what makes this wild from a neuroscience perspective. 212 milliseconds in the first experiment, 214 in the second. That is not the speed of a decision. That is not you thinking, oh, cool, I got a reward. I should be more energetic. That is a signal traveling from sensory input through some deep evaluation circuit and landing in your motor system before your conscious mind even registers what happened. So what circuit could possibly work that fast? This is where dopamine enters the story. And to understand why these researchers think dopamine is the likely culprit, we need to go back to a monkey, a piece of apple, and a discovery that would reshape all of neuroscience. In the 1980s, a neuroscientist named Wolfram Schultz was recording from dopamine neurons in monkey brains. He expected them to fire during movements. They did not. Instead, they fired at the exact moment an unexpected reward appeared. Over the next decade, Schultz and his colleagues worked out the full pattern. Unexpected reward? Dopamine burst. Fully expected reward? Nothing. Expected reward that does not come? Dopamine dip. The neurons were not coding for pleasure. They were coding for surprise. The difference between what you got and what you predicted. This became one of the most important discoveries in modern neuroscience. Schultz and his collaborators won the Brain Prize in 2017 for it. Now separately, a computational neuroscientist named Yael Niv proposed something in 2007 that connects directly to this new study. She argued that dopamine does not just teach your brain what to value. It controls how vigorously you act on those values. Her logic was economic. Every second you spend moving slowly is a second of lost potential reward. In environments where rewards are plentiful, your brain should speed everything up. When things are bleak, why waste energy? Niv proposed that baseline dopamine levels basically set a vigor dial for your whole body, and then there is Reza Shadmehr at Johns Hopkins, who co-authored a book with Ahmed called Vigor, Neuroeconomics of Movement Control. His argument is that movement speed is never random. Your brain is constantly running an optimization. How much is this goal worth to me? How much energy will it cost to get there fast? How much am I losing by being slow? And the output of that equation is how quickly you move. Shadmehr put it in a way I think is kind of beautiful. He said that through the vigor with which we move, we unwittingly reveal one of our well-guarded secrets, how much we value the object of our attention. So you have got these three threads. Dopamine encodes surprise. Dopamine controls vigor, and vigor reveals value. What was missing was proof that in humans, the fast surprise signal, the one Schultz found in monkeys, actually shows up in real-time movement. Not average speed over many trials, not reaction time to press a button, but a within-movement, sub-second change in how fast your arm is traveling, right after something unexpected happens. That is exactly what this new paper delivers. And this opens up some genuinely mind-bending implications. Think about flow states. You know that feeling when an athlete is in the zone, everything clicking, every shot landing? There is a possible self-reinforcing loop here. You perform unexpectedly well, that is a positive prediction error, which triggers a dopamine burst, which speeds up your next movement, which improves your performance, which creates another positive prediction error. Success literally breeds more speed, breeds more success. An upward spiral powered by surprise. And brain imaging actually backs this up. Dopamine reward areas are more active during flow. People with more dopamine receptors in certain brain regions experience flow more often. Now flip it. An athlete chokes under pressure, misses an easy shot. That is a negative prediction error. Movement slows, performance drops. Another miss, another negative signal, another slowdown. Athletes who describe choking often say they felt heavy, frozen, like moving through mud. That might not just be a metaphor. That might be what a negative prediction error spiral physically feels like. And speaking of spirals, there is a darker version of this. Slot machines. Think about what a slot machine actually is from your dopamine system's perspective. It is a reward prediction error generator. A modern slot machine produces 300 to 500 events in a 30-minute session. Each spin is a new prediction, a new outcome, a new error signal. And research has shown that dopamine neurons fire most intensely not at guaranteed rewards, but at 50% probability, which is almost exactly what slot machines approximate. Near misses activate reward circuitry almost like wins. Multi-line machines even create what researchers call losses disguised as wins. where celebratory sounds play even when you lost money, manufacturing false positive surprise signals. So if positive prediction errors physically speed you up, then a slot machine win should make you pull the lever faster. And it does. Research confirms that gamblers on winning streaks respond faster and bet more aggressively. The so-called hot hand in gambling might partly be a literal physical phenomenon. Wins produce dopamine surges that increase movement vigor, which shortens the time to the next bet, which compresses the whole reward cycle. Drugs of addiction take this even further. Schultz himself pointed out that unlike natural rewards, where prediction errors shrink as you learn to expect them, drugs produce a positive prediction error every single time. The pharmacological effect bypasses the prediction mechanism entirely, so the signal never adapts, never weakens. Every hit is a surprise to your dopamine system, even if you, the person, know exactly what is coming, which means every hit perpetually invigorates drug-seeking behavior. The addict is literally accelerating toward the next dose, propelled by a system that was designed to help our ancestors find berries. Now let me talk about why this matters medically, because this might be the part with the biggest long-term impact. Parkinson's disease destroys the exact dopamine neurons we have been talking about. The hallmark symptom is bradykinesia, which literally means slow movement. And for decades, the assumption was that Parkinson's patients move slowly because they cannot move fast. Their hardware is broken. But a remarkable study in 2007 by Massoni, Christova, and Krakauer showed something surprising. When Parkinson's patients were forced to make fast movements, they could. Their muscles worked fine. They just chose not to. Bradykinesia seems to be an implicit decision, not a hardware failure. The brain's cost-benefit math shifts because dopamine depletion makes effort feel more expensive and reward less motivating. A follow-up study in 2024 found that newly diagnosed, untreated Parkinson's patients showed no normal speed increase when rewards got bigger. Their vigor dial was stuck. Only after sustained dopamine replacement therapy did the connection between motivation and movement speed come back online. And even then, only with chronic treatment, not a single dose. Now think about what the new study implies. If you can measure someone's vigor response to unexpected rewards with a simple robotic arm task, you potentially have a non-invasive window into how their dopamine system is functioning. Track that over months or years, and you might detect dopamine decline before any visible symptoms appear. Years before the tremor starts. Years before a diagnosis. Depression fits into this picture too. Severe depression has this quality called psychomotor retardation. Everything slows down. Patients describe it as feeling submerged in water, and neurochemical research links it directly to disrupted dopamine signaling. If depression chronically dampens your prediction errors, if nothing ever feels better than expected, then your vigor system is receiving a constant slowdown signal. The leaden feeling is not just in your head, it is in your muscles, your gait, the speed of your hand reaching for the doorknob. Ahmed said something that stuck with me. If you have had a good day, you will go faster. If you have had a bad day, you will move slower. It is basically that skip in your step. Okay, but I want to be honest about the limits of this study because that is where the real science lives. First and most importantly, they did not measure any dopamine. Zero. The title of the paper says dopaminergic signatures, and the whole framework is built around dopamine. But no dopamine was recorded, injected, or blocked in this experiment. The connection to dopamine is based on the pattern matching, the timing fits, the prediction error structure fits, the scaling fits. It is compelling, but it is indirect. Ahmed herself said, "We cannot show definitively what is behind that burst of energy." Second, the effect is tiny. The researchers themselves call it subtle, not visible to the naked eye. You needed a precision robot sampling at 1,000 times per second and advanced statistical techniques borrowed from brain imaging to even detect it. So nobody is getting superpowers from this. Third, all the participants were young, healthy adults doing an artificial reaching task for beeps and flashes. Whether this translates to real-world movements, older people, people with neurological conditions, or more meaningful rewards is an open question. And fourth, there is a genuinely complicating finding from a mouse study published just 2 months before this one. Nicholas Trich's lab at NYU used optogenetics to directly turn dopamine neurons on and off during mouse forelimb movements, and they found that those sub-second dopamine changes were, and I am paraphrasing, neither required nor sufficient for determining movement vigor. Trich had a great way of putting it. He said dopamine seems to function more like engine oil than a throttle, essential for the system to run, but not the signal that determines how fast each action goes. Now, these are different species, different tasks, different methods. The mouse study manipulated dopamine during routine movement, while the human study tracked behavior linked to reward surprise. So they are not necessarily contradictory, but it does mean the clean story of dopamine burst equals instant speed boost is probably more complicated than any single study can capture. And honestly, that makes it more interesting, not less. Here is something I have not mentioned yet that might be the most unsettling part of all of this. In 2007, a researcher named Matthias Pesiglione ran an experiment where he flashed images of coins on a screen for 17 milliseconds. That is way below the threshold of conscious perception. People literally could not tell you which coin they saw. But when the invisible coin was worth more, they squeezed a hand grip harder. Their bodies responded to reward value they could not consciously perceive. A follow-up found that when the subliminal coin was shown to just one eye, people squeezed harder only with the hand on that side. Half their body was more energized than the other half, and they had no idea. Your movements are broadcasting information about your internal reward state that you have no access to. Your body keeps a score your mind cannot read, and that is what this new study plugs into. The 220 millisecond speed boost after surprise. The way your arm moves faster when something unexpectedly good happens and slower when something unexpectedly bad happens. The fact that certainty produces no change at all, these are not quirks. They are readouts of a system that evolved millions of years ago to solve a simple problem. When the environment is generous and surprising, move fast, capture more. When it disappoints, conserve energy. Every reach for your coffee, every step toward a meeting, every swipe on your phone, your dopamine system is evaluating the world in real time and writing its verdict into your muscles before you even know the question was asked. Movements are a window to the mind, and we just got a new way to look through it. If you want more of the latest science that rewrites what we thought we knew, there is always something new worth questioning.